get one of our old first shirts and a copy of Scientia. So congrats, Luke. So now we just have a few announcements for you guys. One big thing is we do have an officer position available. It's a treasurer position, and these applications are due tomorrow night by 9 p.m. If you're, money or business minded at all, this would be a great position for you to apply to. Or if you're just really passionate about BURST and want to serve this community and want to take a more direct role in planning BURST activities, I would definitely encourage you guys to apply. It's a great way to be more involved and give back to the members in BURST.
Okay, so just a reminder that everybody's last day for points is next Wednesday, the 25th. So a minimum of 16 points needs to be earned by the end of the semester to remain an active member for next semester. And you guys know the drill. There's 4 different categories. You need 7 points for general events and 4 points for both journal clubs and service events, and the RID event has already been completed. And if you're a part of a research lab this semester, you're welcome to fill out the form that's linked in the slide to earn 6 points of research credit.
There are only 2 journal club opportunities left for this semester.
All right, so seniors, if you have been involved in research for about 4 semesters or for 3 semesters and a summer internship, you can receive the certificate. So you can see the link once the slides are sent out tonight to apply for that. And if you're graduating in December, be sure to fill out the form that is also linked in the slides if you want a BURST graduation cord.
Okay guys, so the BURST research recap is finally here. It was previously called the newsletter that we did last year. And there's a lot of cool information in it. The scientific committee has been working on it all semester. You guys may have heard of the Moderna vaccine trials that have recently been on the news. So we had the opportunity to interview Dr. El Sally, who's a co-PI on the phase 3 trials. And we also have spotlights with the Baylor Goldwater Scholars and a lot of cool student researchers at Baylor and important internship deadlines. So if you're interested, definitely check it out. The link is on here and on the weekly emails.
And as always, Scientia submissions for 2021 are officially open. So if you know anyone doing cool research who has an article that's ready to be published, they can send it our way for it to be published in our student scientific journal. Remember, we do accept abstracts as well as original research and review papers. And so if you want to learn any more information, you can go to our website, www.baylorscientia.org.
So we have our last posting social today, and it's a really fun Jeopardy game over Thanksgiving, Christmas, and a nice 2020 recap. Keep in touch with your family groups over the break. We're gonna keep going with that next semester and add some fun events with that. But yeah, make sure to stop by for the social after.
Hi everybody, so also make sure to fill out our end of the semester survey. It's really beneficial for us to just see how all the different programs and all the things that BURST offers is doing for you guys. So you can just scan the QR code on the screen, and it's also linked in our previous email. And you should be able to get 1 free point, and that can apply anywhere.
All right, so we have our final academic workshop of this semester. I'm really excited to put this till the very end. It is the Introduction to Coding for Python and C++ languages specifically. This one will be hosted on Monday, the 23rd at 5:30 to 6:30 p.m. Central Time. And the Zoom link will be put on our social medias as well as our Sunday emails. And so for this workshop, I've been working really closely with the guest speakers. And so we prepared something really engaging and interactive for you guys. So hopefully it'll be really fun while you learn. And so if you have any time, even just for 1 hour to spare for this coding workshop, be sure to stop by. This is really important for lab research skills and also a life skill in general. And so they'll be going over the basics and history of Python and C++, as well as giving you resources and online classes for starting your own coding journey. And so next semester, we'll be going over Java and R, so we'll break apart these workshops and give more time to each of these languages. All right, so without further ado, I will now be introducing our final general meetings guest speaker. So we're really honored to have Dr. Cyran be our final general meeting speaker for this semester. Dr. Cyran's research entails molecular level understanding of chemical and physical processes at interfaces and in complex three-dimensional environments. And Dr. Cyran has just established her research group around this year. So if you also have any interest in her research, feel free to reach out to her after the meeting as well. She'll be also giving ample advice for research, graduate school processes, and some cool anecdotes about her work abroad. So without further ado, I will now hand it over to Dr. Cyran.
Great, thank you so much. Thank you for this invitation. I'm really honored to be here and to share a little bit to you about some of my previous work experience, what the group is kind of in the process of doing now, and again, yeah, some maybe interesting things to answer some questions about graduate school or even my experience abroad. And so today, it's kind of a broader topic, just to make sure we bring people in from all different levels. And so I'll be talking about surface chemistry at environmentally relevant interfaces. So this is something that I am bringing here for my group to do. And like it was mentioned, my group actually started in January 2020. It was an interesting time to start, but we are getting things up and rolling. And so I can also go into a little bit about what specifically undergraduates have been doing in the lab so far. But before getting into this, I'd like to give you a little bit of information about my academic background. And so I grew up in Pennsylvania, and I went to a small liberal arts school called Allegheny College, basically close to Erie, Pennsylvania. There I was introduced, even as an undergraduate student, into research. I started actually the summer after my freshman year, and this really caught my attention and my interest, and so I continued then ever since then. My work as an undergraduate researcher was actually focused a little bit more on biochemistry. So there I was looking at actually RNA experiments and trying to figure out different secondary structures for different RNA hairpin loops. And then from my undergraduate experience, I then went to graduate school at Colorado State University. There I was actually focused more than on physical chemistry. I started in a lab with a new professor, and that was a really great experience. So it gave me the opportunity to build up a lab and learn everything from basically the start. So that was a great lab to be in. And the reason I chose Colorado State is, and this is something I really suggest for everyone that is applying for graduate school, is to make sure that you have, at least 2 advisors there that you're interested in their research, because sometimes what happens is we do different rotations and not everybody can get into their first choice of their lab. And so as a chemistry student, I highly recommend, if this is the case for where you're applying for graduate school, it's great to have options at that school for research that you're interested in. And so that's why I picked to go to Colorado State, is there was a lot of research that I could really find that connected well with my interests. And I had a great time with my learning from my PhD mentor, Amber Crummell. Then after my graduate work, I did go then abroad. I went to Germany. I worked at the Max Planck Institute for Polymer Research. I am not a polymer chemist, but the way they name their institutes is a little bit more historic. I was there for about 3.5 years, and I loved every moment of it. Living abroad was definitely a very interesting experience, and not only from the research side, but then also just from the cultural side and everyday life. So just a little bit about my experience abroad. So how this all started to basically happen is that I applied for an Alexander von Humboldt fellowship. And what this fellowship allowed me to do was actually to conduct research then in Germany. And the nice thing about this Alexander von Humboldt fellowship is that it is open to all humanities and sciences. And so there's actually, it's just a great opportunity for anybody from abroad to go to Germany. For 2 years is how long the fellowship lasts. And then they also have an exiting one, so Germans can then go to a different area of the country or the world in order to do research. The cool thing about this too is that they not only wanted to fund the research, but they also wanted you to have the cultural experience. And so here I was able to take language courses. So I actually lived with a host family for 2 months, and I took an intensive German course in order to learn German. And so the language, I should say, is not a barrier. So at work, we always spoke English, but it definitely did help to know the language to get by a little bit day to day, you know, in case of ordering food and things like that. So I was definitely grateful for the language courses and learned a lot in a very short period of time, and can now understand and speak German a bit. The other thing I just want to kind of show you about, like, something else I was able to experience that you might not think of in a day-to-day basis, but just going and looking at different ways people celebrate PhD defenses. And so the picture on the left is actually a defense ceremony in the Netherlands, in Amsterdam. And it's a very formal process, and they have very strict rules, and so it was, and a very strict time cutoff too. And so that was very cool to be a part of an experience like that. And then on the right-hand side, that's a picture of a PhD defense in Germany. And so it's very common in these cases to have a cart that your colleagues decorate for, you know, it's related to your science and just, you know, the fun parts of your PhD. And so I think it's a really interesting way to celebrate and kind of show your whole defense onto this card, and they actually go around campus and show everybody it. So it was a really neat tradition, and this was just an example of one of the experiences I received by doing a postdoc abroad. And I'd be happy to answer any questions about graduate school or postdocing or just being abroad at the end as well. So now I want to get into a little bit about the work that I do. And so as I mentioned, we're going to be talking a little bit about surface chemistry. And the reason we care about surface chemistry is because there are certain chemical and physical processes that only occur at interfaces. And some of these you probably see in your day-to-day life, but might not have realized. So one of these is actually corrosion. So this is a case where you have a metal that oxidizes. So you can see here, and so maybe you've seen this on your bike chain where you start to see rust, or on some other metal that kind of is in the elements. Another physical process is weathering and dissolution. And so this is more for geological processes. And you can usually see this type of thing with erosion whenever you think about minerals or rocks in this case. Some other processes or physical phenomena are surface tension. So if we look at this water strider, it's actually more dense than the water itself, but due to surface tension, it can actually stay afloat water. And that's only something that can happen at an interface. And the last one here is an absorption process. And so this is looking at, here we're looking at condensation on a window, but this could be absorption of anything. It doesn't necessarily have to be water, but this was just one example. And so what I'm interested in is I want to understand what chemical processes or physical processes are occurring at interfaces and how this differs from the bulk. So when we think about bulk, you know, we can think about our can of water here. And so the bulk would actually be what's happening inside the majority of this, right? And so the surface would only be, in this case, the top layers. So in order to understand surface chemistry and these types of processes, we need two different things. So the first is we need chemical specificity. We need to understand what the molecules are doing at the interface, and we need a way to probe the molecules specifically. The second thing is we need the surface specificity, right? I just mentioned about how we have this bulk scenario as well as the surface. And since we have so much more bulk than we do just surface water, for instance, we want to have a technique or a way to look at only a surface in this case. So how do we do this? Well, the first thing is molecular specification. And so how we do this is we use molecular vibrations. So if you were potentially in maybe in general chemistry, you might go over this, and as well as in organic chemistry, you probably have heard about molecular vibrations. And so what these are is that every molecule basically wiggles and jiggles in a specific way. And we can tell a lot about what makes up these molecules by how they move, and as well as their structure in this case. And so you can think about molecular vibrations as in terms of their chemical bonds. And this is just like a spring. So you think about this, that these molecules or these atoms are vibrating, and how they are vibrating or oscillating depends on the atoms that they're composed of, as well as the chemical bond. And so you can see here, for instance, the water stretching vibration is moving, faster than, for instance, this carbonyl or this CO group here. And so we can use the way that these move in order to tell us about the molecules. And so, as I mentioned, these vibrations are dependent upon the atoms that make them up. And these are typically called, or you might have heard of them as functional groups. And so there's different types of motions. And so here we're looking at a bunch of different functional groups, and we're just considering a stretching motion. So just something where we have, just one oscillator, in this case, OH or CH, it's basically a stretching motion like this. What we can see is that these motions differ in terms of their frequency, right? So how fast they're oscillating will be changing depending upon what is making them up. We can also look at other motions as well. So in this case, the bending motion. And so a bending motion is where you have it's more of like a wagging in this case. And it is composed then of typically more than 2 atoms. But here you can see that these frequencies change not only in terms of what molecules are making them up, but also in terms of what type of motion they are making. And so right now we have this in terms of frequency, but we can also think about this in terms of light. So we can think about it in terms of wavelength. So here I've plotted that, just doing the conversion. And then whenever we think usually, or whenever we're looking at vibrational spectroscopy, vibrational spectroscopists use this weird, this weird unit that's called wave number. And so this is how the data I'll talk about today is shown. And you might also see this in the literature as well. But know that you can always convert between wavelength and wave number. It's just a nice idea to be able to think about what this means in terms of light. So like I mentioned, we wanted to look at this specifically in terms of light. So here what we're doing is we're looking at here just a hydrogen bonded water network, and I have plotted on this side just the electromagnetic field in terms of the frequency or the wavelength of the light. What we're going to be talking about today with the spectroscopy, or with this vibrational spectroscopy, is infrared light. So a very small portion of the electromagnetic field is responsible for looking at the vibrations of molecules. Oops. Oh, sorry. Sorry, that's in the way. I'll just delete it. Sorry for the technical difficulty. With the Zoom, I can't find it. There we go. Okay, so we know now that we want to be able to use these molecular vibrations, and we know that if they're composed of different atoms, we can then tell the difference between the molecules and how they're vibrating. What's also interesting is we can look at how the bonding strength differs as well, and use this as a marker as the molecular vibrations too. And so here's an example, again, of the hydrogen bonded network of water. And what we can see on the right-hand side is that as these oxygens of the water molecules get further and further apart, the frequency that's plotted on the y-axis, we can see that we see a difference in the frequency at which these vibrations will be. And so what's cool is we can use this as a marker to tell us about the local environment of these water molecules, or molecules in contact with those as well. And we can see how this environment changes. And you can think about this in terms of a hydration shell for proteins, for instance, and how this affects the protein structure and what it includes and how it helps basically the protein's function is a way that you can use hydration shell water in order to look and to tell you more about the structure itself. And so this was then the way that we can get molecular specificity. So we use these molecular vibrations to tell us basically what are the molecules or how the molecules are interacting, and to basically be able to distinguish between them as well. The next part that I wanted to show is that we needed the surface specificity. And so in this case, we use a different technique that you might not have heard of, and this is called some frequency generation spectroscopy. So in this case, we're using this infrared light source, which is exactly what I had talked about previously, which is what basically starts or ignites this oscillation or gives us this vibrational specificity. With some frequency generation spectroscopy, we also then overlap a visible beam, in this case with our IR beam. And what this does is when we have these two overlapped basically in space and in time, we can generate some frequency generation beam or a pulse in this case. And what's cool about this SFG pulse that's generated here is that due to its selection rules, so these are the selection rules, it is only generated at a place where you have a break in the symmetry. And so a break in the symmetry, you can think about this as being in certain crystals, but this break in the symmetry is inherently also at an interface. You can think about if we have, again, with my water here. So the surface of the water is different than the air above it, right? And so basically at that surface, we can generate an SFG signal because there's a break in that symmetry. In the bulk, this SFG signal is prohibited or forbidden. And so you do not generate an SFG signal within a bulk solution. And so in this way, we can eliminate the contributions from the bulk and only look specifically at a surface. And more specifically, we can look at only a monolayer of water molecules that are interacting at a surface. And so this is how we get both our molecular specificity in terms of vibrational spectroscopy and surface specificity by using some frequency generation spectroscopy. And so some of you might have seen or have used an infrared spectrometer before. This is an example of an FTIR instrument. And so if you have used one of these previously, you know that you can go in and it's a commercially available instrument. You can put your sample in and there's software to use this. And so it's a great technique. In the case of FTIR, it's vibrational spectroscopy, but it's not surface specific. So this would be bulk. Whenever we want to do some frequency generation spectroscopy or SFG, we don't have the same luxury as having a commercially available device. And so in this case, we actually have to build the spectrometer ourselves. And this is exactly what we have done so far here at Baylor. And so this is an image I took this morning of the laser lab that I have at Baylor. And as you can see, I should have had someone standing here to show you kind of the size difference, but these laser tables are huge, right? So the spectrometer itself is not very condensed in this case, but in order to generate these pulses that we need, so this visible pulse and this IR pulse, we use a laser system here, and then what we do is we build up using different optical components in order to generate an SFG spectrum. And then after we generate the SFG, we then collect it on a CCD camera. I am very excited to say that we actually, 2 weeks ago, we generated SFG. And so we're very excited to then get started to look at different interfaces from here. And so this is just an example of what the laser lab here at Baylor looks like. And obviously you can see it's quite large, a spectrometer compared to that of an FTIR. So let's get into a little bit about what the SFG spectrum looks like. So I can tell, so when we go into the results that I'm showing, to give you an idea of how to read the spectrum and then also what information we can get out. So here I'm plotting the SFG intensity versus the wave number. As we said in vibrational spectroscopy, this is a commonly used a unit of measure. And so here what we see are basically two main features. So here at the lower frequency or the lower wave number region, this is, this peak is originating from molecules at so this is the spectrum of the air-water interface. And these molecules in this lower frequency region, or these vibrations, are coming from the hydrogen bonded water molecules. So you can look here at this image over here, and all of the molecules that have a hydrogen bonded partner, that's where this signal is then originating from. What's interesting, and something that you do not see in FTIR, is this higher frequency peak here, this peak at 3,700 wave numbers. This peak is actually coming from OH stretch vibrations that are coming from water molecules that have no hydrogen bonded partner. So here you can see there's one here in this illustration. And so these are these OH molecules where, you know, you can think there's no extra weight on them holding them down. And so that's what gives them a different frequency. This is also showing you the surface specificity, because we can actually look then at OH stretch molecules where the hydrogen bonded network is cleaved in a way. So this is specifically at the interface that we can see these OH, these free OH molecules. And because of the the similar intensity for both the hydrogen bonded and the free OH, we can show the surface specificity specifically at the air water interface. So now I want to get into a little bit about some work that I had done as a postdoc, and then this is also some of the interest in my group in general. So we want to be able to use some frequency generation spectroscopy in order to study environmentally and atmospherically relevant interfaces. So specifically, we want to look, you know, at chemical reactions happening on water surfaces, and we also want to look at things that are happening on ice surfaces. But I should also mention here that some frequency generation isn't only used for these are just kind of the interest of my group, but you can actually use some frequency generation spectroscopy to look at biochemistry, so proteins at interfaces as well. People have also started to look at using the spectroscopy for catalysis or solar cell conversion and things like that too. And so I'm just showing you one application of this spectroscopy, but it can be applied to different areas as well. So the research that I'm going to talk about today is, this is actually one of the last projects I did as a postdoc. And what I wanted to understand is how molecules, particularly atmospheric pollutants, are interacting with different interfaces. And so one thing we have everywhere around the world is that everything we do basically creates some type of pollution or releases some gas into the environment. And what can happen is basically we can have different chemical reactions happening because of the sunlight, or depending upon how they're interacting with water, or you can think oceans and things like this. We can get a lot of different side reactions that occur, releasing then potentially toxic and harmful pollutants into the atmosphere. And so what I wanted to understand is how trace gases can absorb onto ice surfaces. And so what I looked at specifically are molecules that are known to be large hydroxyl radical contributors. And in this case, it was acetone. And so here I have a schematic of acetone itself. And what I wanted to understand is, how does this interact then or absorb onto ice surfaces? And so I know what you're thinking, we're in Texas, why do we care about ice? It's never really here, right? Well, ice is actually found also in clouds, and you probably have seen those everywhere. And so what actually is in clouds is mixed particles. So there's usually mixed in terms of like ice as well as water droplets in this case. And these mixed particles in terms of ice or water, they can actually be used as a transportation system then for these chemicals or these toxic pollutants. And so what climate change, models for climate change have is they parameterize how clouds can basically be used as transportation systems. And one thing is, or the parameter that is kind of lacking, is how do, on a microscopic scale, how do these molecules interact with ice or water, and then what can that mean for the environment, and what kind of reactions can occur. And so what I wanted to do is look at how acetone absorbs onto water and ice surfaces to get an idea of basically, what kind of chemical reactions could then occur at these interfaces. And so to get started, the first thing we had to do is actually grow single crystalline ice. And this is something we actually do here at Baylor as well. And the reason we want to grow single crystalline ice is this gives us a way to gives us reproducible samples. And so what is single crystalline ice? So in this case, we're growing hexagonal ice. Hexagonal ice is the only form of ice that can form at basically, atmospheric pressure and temperatures that are seen in the stratosphere. There's actually plenty of different types of ice actually. So I don't know, maybe you've heard or read about that they actually found, water on Mars, and there's also ice in astrochemical properties as well. But in this case, we want to actually look at things that are here mostly in the stratosphere. And so we grow this ice using the Joukowsky method. And what this does is actually, we put a single crystalline ice seed on a copper pin, and then we slowly bring the ice out of a melt of millicue water in this case. And then what we want to do in order to see if it's single crystalline ice, and so you're probably wondering like, okay, I grow ice at home, how can this be different? And so what really happens in this case is that the ice that you're growing in your freezer, for instance, is mostly polycrystalline ice or amorphous ice. So there you have, potentially different domains. You don't take into consideration, not changing, or keeping it very still for crystalline growth, and some other things that we take into consideration. But here is an example of single crystalline ice. So on the left-hand side, that's a piece of single crystalline ice. And then on the right-hand side is a piece of polycrystalline ice. And so the differences you can see is that in the polycrystalline ice, you get these dark parts as well as these light parts. And what these are, what we call is different domains. And the reason that they're giving you this difference in the color is because we have them between two cross polarizers. So this is called a Rigsby stage as well. And what you can do is we can use, so ice is birefringent, and we can use this to our advantage. So as we rotate the ice underneath these cross polarizers, we can see how it refracts basically light in different directions. And then we can tell from here if we have single crystalline or polycrystalline ice. And so what we aim to grow in is obviously on the left-hand side, that would be a sample that we could then use for our spectroscopic analysis. And so I didn't want to get into the details, but I'm more than happy to go into obviously more about how we interface ice obviously with a spectrometer and details like that. But I kind of wanted to just give you a broader overview of the results that we got and what information we could get out of this. And so here what we're looking at is the SFG spectrum now of ice. So here I have in A, this is where I have a flow of 0. What this means is I took the ice into the SFG spectrometer. I took a spectrum where I'm only flowing nitrogen. So I use nitrogen as a carrier gas in order then to later vapor deposit the acetone onto the surface. So I have here at 0 seconds, we can see that we get a spectrum. Here, the peak for the ice-air interface is showing up a little bit shifted from that of water, but what you can see is that we still have then the hydrogen-bonded OH stretch vibrations here. Then what I did is I vapor deposited acetone onto the surface. So I did this in different allotments of time. So here is an example spectrum of 20 seconds flowing of acetone on the surface, and then a flow of 90 seconds of acetone on the surface. Something that might be catching your eye immediately is looking at the growth of a peak at a lower frequency. What this is actually coming from CH vibrations. So these CH vibrations are inherent vibrations of only acetone, right? Water has no CH vibrations. So in this case, I could see specifically the acetone absorbing onto the ice surface by monitoring the CH peak here at lower frequencies. What's also interesting is I looked at then the free OH as well. So here you can see a bit noisier data compared to that nice spectrum I showed you at the beginning. But here is the free OH of single crystalline ice-air interface. And then as I add acetone, we can see that this free OH is also shifting to lower frequencies. So here we start to see that we get this peak at like 3600 as well, and then the signal starts to decrease from there. So what we could tell from these experiments is that, one, we could see that actually acetone was absorbing onto the surface, and two, we could actually get out some information about how the acetone was interacting with the ice surface. So in this case, we have these OH vibrations and that are at the surface, right? And so the reason that this is shifting then to lower frequencies is that you now add the acetone. The acetone starts the hydrogen bond through the carbonyl group to the ice surface, and then it shifts this frequency. And so we could actually see basically the acetone absorption and how it's interacting with the surface specifically with some frequency generation spectroscopy. I should say also, this whole process was a lot of design as well. So this is the first time that we could actually use SFG and a flow cell capability in order to look at the absorption of a molecule onto a surface. And so this is exactly the type of thing that I would like to do here at Baylor as well, in order to look at different molecules absorbing onto ice and water surfaces. So to go into a little bit about what this comparison means and what we can see is what I did is I looked at both water and ice surfaces. So here on the left-hand side, I have the spectra again. So we're looking at ice and then also water as well. And what you can see is that the increase in the CH peak and the spectrums themselves look quite different. And it's crazy, right? Because we're looking at ice, which is OH molecules, our H2O molecules, and water, which is also H2O molecules. But we can see that the surface structure from the spectrum is very, very different, and how the acetone interacts is also very different. So the first thing that I kind of went through is I fit the data in order to extract out some quantitative information. And here on the right-hand side, what I'm plotting is the change and the normalized amplitude versus the flow time. Or in the case of the water, I'm looking at the mole fraction. So in the case of the ice, I was vapor depositing acetone on the surface, but for the water surface, how I did this was just make different concentrations of solutions containing acetone. And then the acetone is on the surface, well, it's distributed in the solution, but you do get acetone also on the surface. What was cool is by analyzing or fitting the data, we could look at how the amplitude or the change in the normalized amplitude changes as a function as the flow time or the mole fraction. So you can think about this as like changing the concentration in this case. So as we increase the concentration or increase the flow time, we could see that the surface of ice in this case was at some point becoming saturated. So at some point we're layering the surface of ice with acetone, and then at some it gets saturated. And so after that, no more acetone is then being absorbed onto the surface, other than our monolayer of molecules that was there. And so this could also give us an indication of the absorption coefficients for different molecules as well. In this case, we only looked at acetone for the moment, or what I only present as acetone, but it shows a unique way in order to get this information, absorption isotherms as well. Another thing you might not be able to see initially by eye from this data is that there's actually changes in the hydrogen bonded region for ice and water whenever we add acetone as well. And so I drew a green line here to kind of guide your eye to show you the shift in the spectrum. So you can see that in terms of the ice data, we see a shift to lower frequency. And in terms of the water data, we see a shift to higher frequency. So what I did on the other side is I plotted this frequency shift versus the flow time or the mole fraction at this point. And what we could see is that, yes, we're seeing that for the ice surface, the hydrogen bonded network molecules is actually, you can think about it in terms of those bonds are getting stronger. And then in case of water, we see that those bonds are getting weaker. And this was super interesting to us and kind of, something we definitely didn't expect. We thought, okay, if we have these molecules on the surface, that the hydrogen bonded network would react in the same way. Again, we're looking at ice, right, and water. It's composed of the same molecules, but seeing the shift was quite interesting. And so the reason for this shift, in some theory, after doing some literature search, we saw that some theory had also seen this in the bulk too, is that in the case of water, whenever you have acetone mixing with water, after you get to certain concentrations, you start to see that you get clustering. So you get acetone molecules clustering together, and you get water molecules clustering together, which then changes their, their vibrations, giving us this shift in the frequency. In terms of ice, we're seeing that the acetone is absorbing onto the surface, and those acetone molecules are interacting specifically then with the ice molecules, or these OH groups at the surface. The reason that this is very important is because what happens is different reactions can occur in the environment based off of, for instance, how molecules can absorb sunlight. And if they have different frequencies, right, they absorb different frequencies of light, which means that the sun can affect or cause reactions differently on ice surfaces than they can on water, because right here we can see that their absorption is different. And so this is, I thought, super interesting, and can actually tell us a lot on why chemical reactions could be occurring, and this can really then help, for instance, add information to climate models. And so that is kind of one of the big topics that I'm interested here at Baylor. And so just to give you a conclusion about the research side, I hoped I have shown you that surfaces and interfaces are unique. We saw that we see different molecules at a surface compared to what we would see at a bulk, and different processes occur at these surfaces. And so this is why there's a lot of interest in looking at only processes that can occur at these interfaces. I hope I've introduced you a little bit to SFG spectroscopy. So this was a surface sensitive technique that allows us to look at the interaction of molecules specifically at an interface. Through the project that I have shown you here, we have seen that there is an absorption of acetone on ice and water surfaces, and that this is very different. So we saw that how the acetone affected the hydrogen bonded network of water was different compared to that of ice. And then this can lead to, again, these different reactions that are occurring on surfaces, and can lead us to looking at potentially different chemistry that's happening on ice versus water surfaces. And so that was all of the work that I had talked about, and it was basically a lot of what I had done in Germany, but I have shown a little bit of what has been happening here at Baylor. So I just did want to give some acknowledgements. So this is a picture, a recent picture of the group, including some rotating students as well. So it's not the whole group at this point. And I just wanted to point out some undergraduates that are here. So I have currently in the group 4 undergraduate students, Josh, Pranav, Miranda, and Courtney. Each working on kind of different projects, but I did want to kind of just give you an idea of, how or what contributions undergrads have made so far in the lab. And if you're, like you mentioned before, if you're interested, we can always talk more about other projects and things that undergrads do. But just to give you an idea of what students have helped with so far in the lab, perfect timing, talking about Python coding for data analysis. So I think that is super that you are having a coding workshop next Monday. It's a phenomenal skill to have. It's something that is very versatile. So even here at Baylor, they teach Python in management courses. You can find them in science courses, so it's very versatile skill set to have. And so students, specifically undergraduate students, have contributed so far to making code for a data analysis in terms of SFG as well as FTIR, and also making different user interfaces to operate the spectrometer. Another thing that students have been doing is a different kind of project, but one thing we're interested in is looking at how molecules get included into ice crystals. And so in this case, undergraduate students, for instance, Josh, has grown single crystalline ice and is able to characterize and orient this ice in the lab. He's also synthesized nanoparticles, which is something we're looking into specifically for these types of doping projects. And I've also had students, specifically undergrads, who've contributed to building the some frequency generation setup. And so this included aligning optics, learning about different optical components and how they basically affect the light, and then how to actually make the setup run. And so without these contributions, I would be very far behind at this point. So they've done phenomenal work. It was actually these 4 undergraduates who had joined the lab first, and now I'm starting to get graduate students in the lab. So it's very exciting, and I was really excited that there was so many phenomenal undergraduate students wanting to do research, and so many ways to incorporate them in as well. I think that is a very strong point here about Baylor, and all of you kind of know this as well, but research experience does go a far way, and so all of you are contributing to that in some way. So I just kind of wanted to give you an idea of what students do or have done currently in the lab, and I'd be happy to answer questions about future projects and things like that too. So I will stop sharing there, and I would be happy to answer any questions. I see there are some in the chat, so I have a few questions. How did you decide to create your own SFG spectroscopy setup? And is there literature that helped you build it? Good question, yeah. So I would say that a lot of the skills that I have gotten to build the SFG setup actually came from my graduate work. So in my graduate studies, I had done also, so this is SFG spectroscopy is a nonlinear technique. And what that means is that in this case, we don't just have one pulse coming in, right? We have the visible and the IR. And so in my graduate work, I'd also done nonlinear spectroscopy, but not surface specific. So I looked at bulk in this case. And so everything I learned there about building a spectrometer really helped in order to build one here. And there is literature for sure that can definitely help a bit in terms of determining angles and kind of making everything work. And so I would say those are kind of the things that help the most, but there's typically not literature that's kind of like a how-to for each step. So there are some parts that you do need to know, but I definitely had a lot of help from, advisors and things like that when I had questions, and I did have experience running this instrument. So it did help then to bring it here to Baylor. So that's a great question. Is this common? It is common in nonlinear spectroscopy to build your own instrument. So perhaps you heard of two-dimensional infrared spectroscopy, or there's also and there's two-dimensional electronic spectroscopy. So typically nonlinear spectroscopies are things that you would build yourself in that case. The nice thing is whenever you build the instrument yourself, you have a lot more flexibility in terms of how the instrument works, and as well as little intricacies for building this. So yeah, that's also a great question. Yeah. Oh, sorry, I don't know if I hit on that. Yeah. So what are some sources of acetone in the environment? And so basically, there's acetone was found to be actually just released into the environment from basically things that we do, so chemical processes that we do, and it was found to be a main contributor to hydroxyl radicals. It is atmospherically relevant, and I wanted to use this as kind of a test molecule too, because it does have a really good or high vapor pressure, so I could be able to actually absorb it onto the surface. But moving forward, things that we would actually want to look at is a little bit more environmentally or atmospherically relevant. So in this case, we would be interested in looking at something like nitric acid or sulfuric acid. So different groups like this are actually found more prevalently in atmospheric conditions, and different sources from that can be from us as well as actually from nature itself. So what gets released into the environment. And so those are kind of where we are targeted now here at Baylor, is to look at ones that are found in different sources. Another thing we're looking at is how pollutants such as polyaromatic hydrocarbons, polyaromatic hydrocarbons. And so these actually come from, for instance, exhaust pipes. So anytime we drive our car and things like that. And so those are the types of pollutants that we're most interested in looking at. Okay, yeah, feel free to keep asking, and you can always unmute yourself to ask as well. How did you decide to pursue a PhD, and did you ever consider industry instead of academic as a career? Great question. Actually, so I had only shown you a version of my academic progression of where I had gone, but I actually, after I graduated from Allegheny College, I worked for a chemical manufacturing company in Madison, Wisconsin. I took these 2 years to kind of find out what type of research I would like to do. Hold on, I'll get my dog real fast. So yeah, I actually went to work for a pharmaceutical, well, it was basically a laboratory that checked pharmaceuticals that are in the market. And so I took this time to actually figure out what I wanted to do. And this, after this experience, I knew that I wanted to do research in terms of development rather than just quality assurance type work. And so from there, I started to realize that I was really interested in spectroscopy, and that's what led me to go and do a PhD at Colorado State. Yeah, any other questions? I also know many of you are applying to graduate school, so if you have any questions about that as well, we can talk. But up to you.
I did have a quick question. How did you decide which graduate school to go to?
Good question, yeah. So the one piece of advice I was given is to make sure that I could see myself working for multiple mentors there, just in case, you know, when you get there, typically, in terms of chemistry, what happens is we get accepted to the graduate school, and then typically you go for a visitation weekend, and then you usually do rotations in different groups to kind of find out which one you would like to work in. And so I chose a school that I could find different people that I could work with, for one thing, and also based off of kind of like their research, where their research was going. And so that was, I think, one of the big things that pulled me to Colorado State specifically. And actually, I joined a new advisors group, right? And when I was applying, she wasn't even really on the list. And so I had gone in thinking, oh yeah, I'd really like to work for this person, you know. And then after doing the rotations, I ended up going with my advisor, Amber Crummell. Just the connection really worked, and I was super interested in her research goals and the research that was happening. And so that's kind of how I picked the school, and then also my advisor. So I definitely suggest picking somewhere that, so that's kind of on the terms of like the academics part, but it's also nice to be in a location that you enjoy. Typically PhD programs are 5 years, so you definitely want to be somewhere that makes you happy and satisfied as well. It is a long process. It can sometimes be quite grueling, I would say, but I think keeping those types of factors in mind can really help you in deciding on which school to go to.
Thank you.
Mm-hmm.
Awesome. Well, thank you so much, Dr. Cyran, for speaking with us tonight. And if anyone has any more questions for Dr. Cyran about her study abroad experience or just her grad school experience, you're welcome to email her, and I'm sure she'd be happy to answer your questions.
Definitely.
All right, well, let me go ahead and share my screen and we can wrap up our general meeting. All right, everyone, so don't forget to connect with us on social media. Today's general meeting will be posted on our YouTube, so you're welcome to rewatch Dr. Cyran's talk if you want to refresh some of the topics. And then follow us on Instagram and Twitter. So here's the sign-in. Thank you all so much for attending our last general meeting of the semester. And hopefully, if you have time, stick around for the post-meeting social that'll be happening. We'll be playing a Jeopardy about Thanksgiving, Christmas, and 2020.